Alrighty, boys and girls, welcome to video lesson 6-3, our lesson on logarithmic functions. Logarithmic functions are the inverse of exponential functions. Okay, so we want to know what the inverse of the exponential function f of x equals b to the x is. We want to know what the inverse of that. Remember, the notation for inverse is f to the negative 1, so that means inverse function of x. So we want to know what that is. We need to flip-flop the x and y like we've been doing all along. So f of x becomes, we got y equals b to the x. So now we're going to the inverse. Now we're going to flip-flop the x and y. So we have x equals b to the y. And now we need to solve. We need to solve this equation for the y. And there is no way, of no way to get that y by itself. Now, as we raise b to the y power, we need to take the inverse of that. And the only way that we can do that is to create a new function called log. So what we have here is we have y is equal to log base b x. And this guy, let me get my pointer, this guy right here, log base b x, y equals, is the inverse of y equals b to the x. Okay, just a couple vocabulary terms. A common log. Our common log is a log with base 10x. Okay, and what we do is we just don't write the log base 10. We just write log x. So if you ever see a log with no base, this means log base 10x, which we call the common log. Okay, and a natural log is log base e of x. So if you ever see, and we write that as ln, so if you ever see an ln x, what that means is log base e x, and we call that the natural log. Okay, let's talk about what the graph of a logarithmic function looks like. To do that, first of all, let's graph y equals 2 to the x. And I'll do that in red. Y equals 2 to the x. And you know that this graph looks like, I have a y-intercept of 0, 1, because 2 to the 0 power is 1, right about there. I'm doing that the best I can. And of course, when x is 1, y is 2. When x is 2, y is 4. This gets big really quick. It shoots up. On the left-hand side, we hug the x-axis because that's my asymptote. And so I have, here is your y equals 2 to the x graph right there in red. I'm going to draw the logarithmic function in green, and of course we know it's going to reflect over the y equals x line right here. So all the ordered pairs, x comma y, are going to regraph as the ordered pair where the x and y flip, y comma x. So the logarithmic function is going to look like this, and we'll do this in green. I have an x-intercept of 1, 0, because that's the reverse of 0, 1. I have an ordered pair 2, 1, because that's the reverse of 1, 2. I have an ordered pair of 4, 2, right about here, because that is the inverse of 2, 4. So this is going to shoot off to the right very quickly, just like in the exponential function. We shot up very quickly. In the logarithmic function, we shoot off to the right very quickly. And now to the left of the x-intercept 1, 0, we have the ordered pair 1/2, -1, 1/4, -2, 1/8, -3, etc. And so we're going to hug the y-axis, and that is our asymptote. So what you got here, as you can see, the logarithmic function hugs the negative y-axis, goes through the ordered pair 1, 0, and then shoots off to the right very quickly, because it's the inverse of the exponential function, which has a y-intercept of 0, 1. It shoots up very quickly, and then it hugs the y-axis on the negative side. So notice in the exponential function, we have an asymptote of the y-axis on the negative side. On the logarithmic function, we have an asymptote of the x-axis. I'm sorry, the y-axis. Did I say x-axis? this should be the x-axis on the negative side, and then the logarithmic function, we have an asymptote on the y-axis, on the negative y-axis, and then it shoots off to the right very quickly. Okay, so we got to think about now, what are the restrictions on our variables? Well, just like in the exponential function, b cannot equal 0, 1, or a negative, because that's what b cannot equal in an exponential function. So the same thing is true in a logarithmic function. The domain of an exponential function is all real numbers. Okay, that's the values of the x in an exponential function. So in the domain of a logarithmic function is going to be the values of the y, which are all positive. So the domain of a logarithmic function, if you look at the graph, is all positive numbers. X is never down here on the negative side. So x are all positives. So x is greater than 0, because it's asymptotic on the y-axis. In the range of a logarithmic function, you can see now it covers the full spectrum of the y values, just like the x values of an exponential function cover the full spectrum. So the range of a logarithmic function is all real numbers. Okay, so we want to write a logarithmic expression in exponential form. Remember now, this is just like the reverse, where the log itself is equal to the exponent, and to transform a logarithmic expression into an exponential expression, basically we're going to draw like a little swirl. So in other words, 3 to the 4th power is equal to 81, and do we see that swirl going around? So 3 to the 4th power is equal to 81. So to write this in exponential form, we're going to say 3 to the 4th is equal to 81. To write a logarithm in exponential form, remember, we're going to flip-flop. So in other words, the logarithm itself is going to equal the exponent. The base is still the same. So we're going to write this as log base 25 of 5 is equal to 1/2. Because if we look now, let me get my pointer. 25 to the 1/2 power is equal to 5. Notice the base of the log up top here was 3. The base of the exponent is still 3. The logarithm is equal to the exponent, so the logarithm is equal to 4. That was the exponent, 3 to the 4th power. 3 to the 4th power is equal to 81. Down here, I have a base of 25. So that's also going to be my log base, log 25. Log base 25. The 5 is my actual, what I'm taking the log of, and my exponent, 1/2, is equal to the log. And if we were to exponentiate this, we can see now that 25 to the 1/2 power is equal to 5. The square root of 25 is 5. Okay, I'm going to give you 5 properties of logs. These are our basic logarithmic properties. The first one says that the log of any base, so log of any base, base b, of 1 is always equal to 0. And the reason that is true is because if I exponentiate, b to the 0 power is equal to 1. Any number b to the 0 power is equal to 1. So the reason for that is any number to the 0 power is equal to 1. And our second one now, log base b, any log of a base b of that same base is equal to 1, and the reason is because if I exponentiate, b to the 1st power is going to equal b. So let me get my marker. B to the 1st power is equal to b. B to the 1st power is equal to b. 1 to the 0 power is equal, b to the 0 power is equal to 1. Okay, numbers 3 and 4. Numbers 3 and 4 are called the inverse properties of log. When you take log base b of b to the x power, that equals x. And again, the reason for that is b to the x power is equal to b to the x. b to the x power is equal to b to the x. b to the x power is equal to b to the x. Okay, if we look at the second one now, if we take an exponent, b raised to the log b to the x power equals x. This is really confusing, we went through this in class, but what this is saying is b to some power, where that power is what we raised b to get x, that's going to equal x. It's confusing with letters here, and we went through it in class, and I'll go through it again, but this is, you just need to, when you see this of an exponent raised to a log, where it's the same base, x, that's going to equal x. Lastly, this is called the exponential property of equality. The exponential property of equality, which just says if log base bx is equal to log base by, so if you have two logs with the same base and they're equal to each other, then x must equal y. In other words, if log base bx is equal to log base by, well, hello, x must equal y. Okay, let's do a little exponent practice here, disguised in some logs. So we're going to think about what I'm asking you is, what do each of these things equal? Okay, what do each of these things equal? So let's think about it this way. Let me get my marker. What I want to know is, what does log base 8 equal? Let's call that x. You can think about it this way now. Let's do our little swirl. 2 to the x power is equal to 8. So 2 to what power is equal to 8? And that answer is 3. 2 to the third is equal to 8. So log base 8 is equal to 3. 2 to what power is equal to 32? Well, this must equal 5. 2 to what power is equal to 256? Whip out your chart, and you recognize, I hope, that 256 is a power of 2. In fact, it's 2 to the 8th, so this equals 2. You guys stop. I'm sorry, what did I say? 2. That equals 8. You guys stop the tape right now. And fill in the rest of these. You can use your power table if you need to, and I shall be right back. Okay, here are your answers. Again, we said the first one was 3 because 2 to the third power is 8. The second one is 5 because 2 to the fifth power is 32. We said the third one was 8 because 2 to the 8th is 256. The fourth one is 5. 3 to the fifth power is 243. Next one is 2. 3 to the second power is 9. The third one is 1/2. Again, we're practicing our exponents here as well. The square root of 9, 9 to the 1/2 is 3. The next one, the seventh one, is 4 because 10 to the fourth power is 10,000. Here we can even use our inverse prop. 10 log of 10. 10 to the fourth is going to be 4. So this is log base x, 4 to the 10. I'm sorry, log base b of b to the x is 4. So 10 to the fourth is equal to 10 to the fourth. This one's our other inverse prop right here. So I have 2 raised to some log of log base 8. Well, this is going to equal 8. We know that log base 8 is 3 because 2 to the third power is 8. So this number right here is 3. So this then becomes 2 to the third power is 8. The next one is -2 because 0.25 is 1/4, which is 1 over 2 squared. So 2 to the -2 is 1/4. The next one is 0 because 3 to the 0 power is 1. And the last one is -8 because 1/2 raised to the -8 power is 256. Hey folks, that's it. I hope you enjoyed yourself. I hope you had as good a time as I did. We shall talk to you soon.